some notes later.
Sorry in advance, Jeff.
Probably don't drink a brewery.
All right, so as far as you students go, you'll have some exposure to this already, especially Kenzie. So just kind of put on your hat of you're a quality control technician in a precast plant, and you don't know anything about design stresses and forces and yield and compressive strength and all that stuff. So the intent of this portion of the class that we're going to teach. So we're going to teach a precast inspection class for the TTCP program, where now the requirement is PCC 1, which you guys just took. And that's all they have to take. There's no reinforcement steel, no plan reading, any of that stuff. So I'm kind of breaking that class into 3 different sections, one for PCC stuff, one for reinforcement stuff, and then one for pre-pour and post-pour inspection. So this section that we're going to talk about today is kind of the reinforcement section, which will ultimately be several hours long, probably a half day or so long. But I'm going to just kind of give the concepts here and see if it makes sense. So again, this is all in my head. I've been trying to figure out how to relate things that everybody's familiar with already to reinforcement in concrete boxes. Jeff, we had a problem a couple of years ago, and Jeff had said, I've been doing this for 20 years and I had no idea why we had that rule that we were doing. So I guess this is my attempt to kind of explain that without going into math calculations and stuff. So I brought a bunch of show and tell stuff. The idea behind that is these are things that we're all familiar with already. And we can use those to kind of demonstrate concepts in design strength. I had planned on having a little bit of time in between the 2 meetings, but we don't, so don't have anything set up here. Bear with me. So I went around my shop this morning and I just grabbed a bunch of stuff and I'm like, oh, that's a good example. That's a good example. We'll see where we go.
The box that never ends.
Why didn't you bring the box over?
Well, the box is part of it. So I just grabbed a piece of rebar. We don't know what that's like. And then I grabbed a few shapes of different things. So first of all, let's talk about a basic theme. So we've all been to PCC 1 class. And this is the one, or one of the very few things anyway, that in PCC 1 that applies to precast, you just don't know that it applies yet. So we make a beam in PCC 1, right? It's a monolithic concrete beam. And then we put it in a beam breaker and we apply a load to the top here, supported here and here. So what happens to that beam when you load it up?
Get a fracture or break
Okay, so where does that start happen?
at the point of contact.
You think it starts here?
This below it.
At the tension point at the bottom.
So
Where
in here.
separates.
Yeah.
So that's where that crack starts. And then it propagates up somewhere in here and then the beam's broken, right? So what's happening? Why does it start at this bottom here? If you could stop it just instantly after it starts, why does it start at the bottom?
Because that is under a tension regime and
Use different words.
okay.
You're the inspector at a precast plant.
Dumb it down a little bit.
I
Down.
think about it in mechanics and materials terms.
Yep, and you can't do that.
Yeah. It's wanting to stretch at that point.
Wanting to stretch at that point, right? So there's some internal forces going on right here, right?
Yeah.
So then, once this is broken this far up, why does it keep going up? Anybody? And why does it happen so fast?
It's a brittle material. Non.
Other
Not
answers?
viscous.
I'm asphalt.
What happens if it's asphalt? What if you did this to an asphalt beam? What would happen?
Crumble.
It would just crumble. It would probably just.
It would do the same thing though, right? It's just a different. material.
In theory, but
So once this starts, let's say this has broken up an inch, right? Now all you really have is a beam that's this big. You don't have this anymore. This is not doing anything, right?
Yeah.
Can we all agree with that? All right, so as the crack goes up,
Your strength is rapidly decreasing.
the beam itself gets thinner and thinner, right? So that's a non-reinforced beam. And what's really happening here is delete this part. So it's just the bottom. We're gonna just leave that bottom crack. And so just like the forces are pulling it apart here when you're loading it, you have compressive forces that are pushing it together here. Right? So it's tension in the top. No, yeah, compression in the top and tension in the bottom, right?
Yeah.
So as this cracks, this section gets smaller, and now this force is in here. And so you have what's called a neutral axis halfway in between there. So if we were to look at all of those forces, the reason that starts cracking at the bottom here and you have the most tension in the top face here is because the forces inside would actually look like, if I drew them to length, right? They would look like this. So they're getting more and more force on the top and bottom surface than at the middle. Does that make sense to everybody? Okay. So I brought all these examples that I wanted to talk about. And this piece of foam is the closest thing I could think of for a monolithic thing, similar to the beam. So when you load it in the same way, you're doing this until it snaps, right? This piece of foam actually has the skin on the top and the bottom, but if I scored that skin, for everything but a knife. So if I scored that skin along the bottom and I loaded it the same way, it's going to break right where I scored it. That's the weak point, right? If it's monolithic, I'm creating a stress point for it to break. So hopefully that'll be explained later. One of the things I thought about as an example for all of this, I'll use this paper as an example of something that's fairly strong, right? Like this. What happens when I open that paper up? When I take the wrapping off of the paper?
I'll just fall essentially.
Does everybody agree with that? It's not gonna stand up like that anymore, is it?
I think it will. I think it will. Paper's
Think it will?
to a point.
All right, so this one's unwrapped. We're gonna do the same thing with this one. Now, there's a couple pieces of tape on here because the paper had ripped prior. Okay, so we have a bunch of sheets of paper, 500 of them, right? And they're wrapped up and it's supporting itself because it's wrapped up. Interestingly, I could not find an unbroken ream of paper. They all were broken.
Oh.
We'll talk about that in just a second. So here
Yeah.
is the same thing that has no wrapping on it.
Yeah.
So why do you think all of the reams of paper in the building were broken?
When you pick them up, they want to rip.
Is there,
Like
Kind of.
is there less strength with length? So the greater the length, the less strength there is?
In a
Like,
way, there's
easier to
more,
buckle.
there's more force you're putting on it, but the reason is because they take them and they take them out of the box by just pulling them out
Yeah,
and throwing them in the thing, and they can't take that, the wrapper can't take that strength, right? The outside skin is what's allowing it to stand up like this, where when the skin is broken, it does this. That's because all of these individual pages aren't held together anymore. They move on each other. That makes sense? So, and the work tiles, exact same thing, right? This is just a bigger example of the paper. That when they're able to move on each other like that, the top, well, let's load it the same way, right? So the top stretches, or the bottom stretches, they move on each other. If you glued them together, they would be solid and more solid and rigid, as solid and rigid as core could be. So again, those are kind of monolithic. It's all the same material, but it's not attached to each other. The reason that we do compressive strength tests in concrete, the reason that we make cylinders, we make beams, and we do the testing is because the whole strength of the material is related to how much compressive force right here it can take. So if it's just sand, the sand grains, or let's say it's just sand and a tiny bit of cement. So it's solid, but a little bit of force is going to break it because it can't take very much compressive force and it can't take hardly any tension force. So what do we do about that? Why do we reinforce concrete? Well, we do that so that it holds it together here in this compressive area. Right? Because if we just had concrete boxes or pipes made out of concrete with no reinforcing steel, what's going to happen? I always wanted them to make a concrete pipe with no reinforcing steel so I could see it in the 3H bearing test, because it just all fall apart, right? There's nothing holding it together, you know. A couple more examples I could think of. Cardboard box, we all touch them every day, right? And it's pretty strong. This is an empty one. I just taped the end back up, but I mean, it could support 50 pounds on top of there if you spread it out. Pretty strong. Where what they're doing to make a piece of cardboard that strong is they have another piece inside of there that spreads these two surfaces out. If you take a piece of cardboard, I guess I have another one here, multiple pieces put together with the corrugations. If you take all of the corrugations out of the cardboard, you just have paper, right?
Mhm.
So if I do this and I crush it all down, maybe. Now it's just two pieces of paper that are held very closely together, but it weakens really quickly as you get those two surfaces closer together. So similar to here, as it starts to break, it's only this big, then this big, then this big, until the whole thing's broken, which happens instantly in the beam breaker. But the concept is still the same. So keeping that in mind, I am working on a project in my home shop, building a camper, and I'm trying to see how light I can build the camper. So people come over and they're like, "What the heck are you doing?" And this is my demonstration piece that I show them. So this weighs virtually nothing, right? It's like 15 pounds for a 4x8 sheet or something like that, almost nothing. Where here, we just broke this in half by scoring it and pushing on it. This has a piece of material on both sides. It's actually wrapped, that's glued, and it makes skin on it. And so with this, you can take and you can put a tremendous amount of pressure on it before it breaks. It will break, but it won't break like this piece will. And that's because the skin here is keeping this, this side, I guess, from pulling apart. That's what this is for. So if you're familiar at all with fiberglass, like not just fiberglass, the material itself, but fiberglass composite construction where they put a skin of fiberglass on the top and bottom of a piece of foam. This is what they call poor man's fiberglass, where you're using a piece of canvas and gluing it on and then adding glue to the surface to create that tension force that resists tearing apart. So it's on both sides. This top side here isn't doing any good. Isn't doing much good. It's the material that's absorbing that compressive force, but the opposite side is the one that's really holding it together. So you can pass that around if you want. So I did another example this morning. I have two pieces of aluminum skin that's, I guess they're two different thicknesses. This is 32 thousandths thick, but it's very flexible. This one's 25 thousandths thick, again, very flexible. And we know what the foam's like, right? So I took these two pieces and some carpet tape to completely adhere them. So they're completely bonded with this piece. So now we have an aluminum composite structure that's, again, incredibly strong, incredibly lightweight. But the whole reason that's possible is because this surface doesn't stretch, and it's the same on both sides. You control it on both sides. So again, in beam theory, that's what we're doing is we're taking all of these forces that get greater and greater as you get further and further away from the neutral axis. He's busy. As you get further from the neutral axis, these forces get bigger. We're putting them all the way to the outside in that example with the aluminum. So that's where the stress is, and that's where you calculate that. So if we're going to put reinforcing in this beam, where do we put it? What's the ideal location to put the reinforcing? No matter what it is, it doesn't matter if it's a skin, it's a rebar, if it's a sheet, whatever. Where do we want it?
Or reinforcement.
Top and bottom.
On both sides,
Right.
yeah.
Top and bottom. And I guess I should get specific on the top and the bottom. So if you're breaking it, like if you're loading it like this, designing it like this, do you want it on the top or the bottom?
Bottom.
If you had one choice, yeah, bottom. So why do we put it on the top too? Top also.
I mean, is it,
Do we care? Why do we care, Natasha? That's what we do. We must care, right? All right, so let's assume that we want to pick this beam up.
Because there's stress, not always on the one side,
right,
it's from different, both sides.
say you had thermal effects on it too, that could affect the whole beam.
That is a design characteristic, is thermal expansion and controlling that. Also, shrinkage from the concrete as it's curing, but
Yeah.
we're not going to get into that. The main reason is if, let's say, there was a hole through here and you're going to use it for a lifting loop, right?
Oh, yeah.
Now, all of a sudden, your load is here and the weight on it. That's what this top steel is for, is to keep it together that direction. So we know if we looked at this from the end now, we know that we want the steel here and here, and that we know that it's important that they can't move on each other like the paper. You guys going?
Yes.
Okay. Just like the paper, they can't move in relation to each other or you lose that strength, right? So that's why we need to keep those from moving. Well, the most efficient way to do that is with a web of material instead of a monolithic slab of material. So I brought a few examples in our everyday life of that. So I-beams. Why are I-beams made that way? because you need the top and bottom surfaces for that compression and tension force. That's what creates that strength. And like I said, I looked around my shop and there was all kinds of examples of that. So looking at vice grips, where is it important that it has strength? It's important on the jaws, but then they have that web. This is kind of more into curved beam theory, but that's why they're designed that way. Reduce the material where they can, because you don't need this. So you reduce the material where you can and keep the material where you need it. And then we see the same thing in this clamp, where we have this outside skin, inside skin, and a web. We need that material for the compression and tension, and then we can hollow it out to either make it lighter or use less material. I have a squeezer tool here where we're putting 22 pounds of force on the end of here.
Squeezer tool.
It's a squeezer. That's what's called, rivet squeezer. We're putting force here. It ends up with 3,000 pounds of force here, and we lighten up the material that we don't need to make the tool lighter. Similarly, here's another yoke that goes on the end of here that has not done that because for ease of manufacturing, it's solid, which is fine. Because we do that with other structures, right? We leave the material, but this is twice as heavy as this one is. So there's different reasons that things are designed that way. And I guess one of my last examples is this square where they have nice surfaces that they want to stay flat. They put a web in here to keep it strong and straight. So any questions about any of that stuff so far? So there's also different shapes, right? We talked about the I-beam shape, but there's squares and rounds that are similar. So how is the square tube and the round pipe similar to the beam?
You're still gonna have the same stresses on top and bottom.
Yeah.
Regardless. But
Why would we want to use a pipe instead of a?
you don't have stress concentration around it. There's no sharp corners on it.
That's a good answer. It's not the one I was thinking of, but what else?
Less material in case of pipes,
It is, that's true. It's less material.
and the neutral axis stays the same.
There we go. That's what I was looking for. So the orientation no longer matters, right? It doesn't matter which direction you're putting the force on.
You don't have a strong axis on it.
Right. If we made, that's why I brought this ruler. So if we made broom handles out of material like this, what would that be like to sweep with? Right?
It wouldn't be.
You'd always have to sweep this direction,
Right.
because it's the only direction that this piece is strong in.
Mhm.
There's another thing that happens as you lose the distance between the two surfaces, and that is that things want to switch. Well, everything wants to switch to its weak axis, even a beam like this.
You have torsion on.
So as you load, this is fairly strong this direction as you put a load on it, but as you load it, it's going to want to twist and flop over to its weak axis. So that's another reason to make it similar in height and width, because then you don't have those problems. Same way. All right, so we know now that this is a compression flange on the top and a tension flange on the bottom. And so let's convert this now into the concept of reinforcing steel in precast. So let me just start over with my drawings here.
You typically have more strain on their bottom flange.
Well, we'll talk about that here in a minute. So again, I'm gonna draw a beam. This is no longer a beam like we make in PCC1 class. This is gonna be a structural beam. Like what do they call those? Vicky, what do they call the pieces on the end of a culvert? Right before the taper section. Lintel beam.
Like an apron,
No, on the top, spans across the top.
a lintel beam?
Yeah, lintel. Lintel's the right. Okay, so if you imagine this is a lintel beam, then this is going to sit on a wall here and a wall here. So very similar to what we were just talking about, where it sits here. Now your forces are spread more evenly across here instead of a single point, but same function. So we have compression on the top, tension on the bottom, and we're going to put a piece of steel here. Well, we just learned that we're going to put steel on the top and the bottom because we have to pick it up, right? We don't want it to break when we pick it up. So how do we determine? We know that the best place to put that steel is on the very outside, right? How do we decide? Well, why don't we just put it on the outside? Let me start with that. It's the best place for it.
Exposure, yeah,
What'll happen if it's exposed?
rust, corrosion.
Weakens, yeah, it goes bad.
Okay, so we have to cover it with something so that it doesn't rust.
Mm.
And that's why it gets cast inside the beam instead of laid on the top. So how far inside does it need to go?
Depends on the structure engineering. How far is it gonna be covered? Is it gonna be covered a quarter inch, half inch to keep the strength that is still required?
As closest to the outside as it can be.
It is, however, you end up with some problems too, like we talked about with the piece that has the aluminum on the outside, taped on the outsides of it. You end up with bonding issues too. So if it's too close to the end, you lose that bond. And so the final answer is check the plans. You know, what does a designer design it for, right? Most of our specs say either an inch or an inch and a half of cover. If you're designing for like a actual structural beam, I think it's 2 inches of cover. And what they're doing there is the more cover you're adding, the more protection you're getting on that steel. So yeah, that's why they go inside. So we also talked about this neutral axis here, going through the middle of this beam. So what happens the closer we talked about that you want the steel as far away from that neutral axis to make it as strong as possible. But what happens as your steel gets closer and closer?
It's less and less.
Less and less what?
Well, the internal force on the steel is less the closer you are to the neutral axis.
And so what happens if they think, well, if an inch of cover is good to protect that steel, let's do 2 inches of cover and that'll really protect the steel. Then what happens?
You're essentially, you're effectively having a smaller beam, a little weaker beam.
Does everybody agree with that? Okay. So yeah, the closer you get to the center, the less effective the steel is. And it's pretty easy to do a mathematical calculation on that.
You want to do a VM diagram real fast?
And it's pretty, no, it's pretty shocking to see if you move that a half an inch, what difference you get. And so I was talking to Jeremy on Friday about some pavements in District 2 on I-35. If you've ever been up there, the overlays are coming apart. It's a mess. There's holes everywhere. But it's original interstate pavement. And we don't see that very often. But when they designed that pavement, it was an 11-inch section, I think he said, 11 inches deep. And it's fully reinforced. So they had rebar going each direction in a mat through there. And it looks exactly like that, just roughly to scale. So what's wrong with that picture based on what we just learned?
Your rebar is running through your neutral axis.
It's not doing any good for strength, right?
Yeah.
It's keeping it together. It's
Mhm.
keeping it from breaking apart. But when you load this with a tire,
You're still going to get fractures and cracks and things.
this part of the pavement shouldn't even be there, right? It doesn't matter. So now you have, instead of an 11-inch section, you have a 5.5-inch section. So they figured this out shortly after they were building the roads this way. And they came back and they put asphalt overlay on them. So they've added, I think 4.5 is what he said here, to the top of that. So now what did it do?
Why would they do that?
Well, we just talked about it with the layers of aluminum and
Well, essentially it would make it stronger because you're moving that neutral point.
you move the neutral axis now to right
Yeah.
here, right? So great solution. What then happened, like we so often do, is we don't take care of what we put out there. It gets cracks in it, it gets sun damage, it gets old, it starts falling apart. So then we put a microsurfacing layer on it to try and protect it, but we did it too late. We did it after the asphalt was all dry, it was crumbling already. We lost the support. And so then this piece flexes, it becomes a mess, and then they came over and they put a second overlay on it. And now you have, if you've driven up there, you know what I'm talking about. It's like you dodge the holes in these microsurfaces. But the whole concept was great. They just screwed it up when they did this. So in the very beginning, before they built all this, they would have put steel in the bottom 2 inches or so. Now the neutral axis is, well, that's not quite right. It would be about there, right? And it would quit fracture. The original slab wouldn't have fractured the way it did. So that's a great example of how when somebody thinks, oh, we'll put it in the middle instead of the bottom third or whatever the design said, where they get the wrong thing. So another similar example, I had a friend who is a concrete guy, and he's building a safe room for a client. So he says, I need a suspended slab over the safe room that is, the size is this by this. So I did the math, I did the calculations. I said, you need to put, trying to remember, oh, there's a center wall. Okay, that makes a difference too, because it changes the forces. But there was a center wall, and because of that center wall, he needed steel here. So I told him the spacing, told him where it needed to go. So this is a 6-inch slab. They didn't want to spend more money to do an 8-inch slab. 6-inch slab, an inch of cover, top and bottom, calculated out to be such and such bar size, such and such spacing. Like I said, the center wall makes it a little funky. That's the reason for the top steel. We're not going to get into that. But what they did is they put blocks on the ground that suspended this mat. And that's what we normally see when they're pouring a slab in a precast plant, right? There's chairs that it sits on. That's great. And then what did they do? They took these other bars. It's harder to suspend that, right? It's harder to suspend that at 5 inches or whatever it needed to be.
Mhm.
So they poured this, stomping around on the steel as they're pouring it, because that's what you do when you're pouring concrete, right? So in between where all these chairs are it's getting pushed down. Maybe the chairs are falling out. We don't know what's happening. Then for the top steel, they drop the steel bars on top every 12 inches. And they take a shovel with a piece of tape on it and they push them down to where they're supposed to be. And so he tells me after the fact of, how they did that. And I'm just like, oh my gosh, I'm terrified, to know. And this is the slab that then is like a den or, some type of living space over the top of it.
It all depends on how
Which
coarse the concrete is.
you just don't know, right? You don't know.
Right, there's a lot of information.
You can figure this out and you can say, well, this will make it, and then you can add a safety factor for when they do screw it up. But you never know how bad they screwed it up, and there's no way to test it.
Because that's what they're doing with the top is nowadays they do the same thing, except for they vibrate the top down instead of just push it down. So just depends on the plasticity of the concrete, and
Yep.
there you keep going down that path.
And so, and that's again where the concrete strength makes a difference. It's not that we're ever going to crush this stuff in a vertical way that we need 2,500 pounds or it's going to turn into powder. It's because we're putting steel in there and we're trying to bend it different directions, and without the compressive strength that resists that, or without the resistance for that compressive strength, it crumbles and it bends and you've lost your strength anyway. So again, we're talking about neutral axis and where that neutral axis is. Those are just some examples of a couple real world things I know about that they can mess it up and it changes everything. So in the shop drawings, we want to see what that cover is supposed to be. We also want to see what the distance between in precast world, the cages are, and we want that to be correct. So if we're looking down on a precast box mold, we have the center mold, we have the outside mold, and then these boxes on the inside, or the cages on the inside of this. Addison and I were at a place a few weeks ago, and the steel here was too close, and then it was too far over here, right? So now you can start seeing the ramifications of when that steel box is not in the right place, what can happen when you start loading it. So now let's talk about, we have this beam, we know it's designed right, we know the steel's in the right place. Now we're going to turn the beam into a box. So where before this beam was sitting on the sidewall, now we're going to cast it into the sidewall, or in with the sidewall. So let's just pretend like it doesn't have a bottom. So now what happens? When we load this top piece, let's pretend like it's not an earth load. Let's pretend like it's a point load just for ease. So what happens when we put our tire right in the middle of it? Or before it was supported on the ends, it's going to bend like this. What happens to this? Ideas?
It's a frame.
No engineering ideas, just kind of general ideas.
I think I know what you.
So if I was to do this out of my foam stuff, right? I'm making my camper, right? And I put an air conditioning unit in the middle of the top foam lid on the wall.
Bow.
What's going to happen right here?
The walls start bowing
Going which way?
out.
So like this.
Yes.
Okay, so it's going to make these walls bow like this, right? So that's what we call inducing a moment around the corner into the wall. So because this is attached here, as this is cranking up, it's going to try and pull that wall out. So what do you think we need right here to resist that?
So that's your weakest point. So you're going to strengthen it up with something to
So
make it stronger.
if this is your beam,
Yep.
and this is your load, you're putting steel in right there to resist that tensile force, right? Now, what happens when, let me draw this straight again. what happens when you backfill it? And you put all this in, what's gonna happen down here or to that wall in general?
Probably gonna change the direction of the way it wants to.
So now it's gonna wanna bow this way,
Correct.
right? So that's when we put steel in this. So now, last piece. Now we're gonna cast this all together into a box. So when I load it in the top, what happens over here?
Goes out.
Gonna go this way. What happens down here?
The corners will be the,
So that because this is strong, this twists this way, right? And bows up. Now you also have the weight of the box sitting on the ground. And assuming that it's not coming up out of the ground, we have things up here, right? So we have that and that going on. So here, because of the force here, we're gonna put steel in here. And because it's gonna be torqued the other direction, we're gonna have steel here, but it's a different amount. It's a different amount because of the weight of the box and the earth load than it is from the top load from the side load. So there's loading everywhere on this box.
so why you put steel in it? Why just make it thicker?
Well, what happens when you get a crack?
But it's thicker. It'll last longer before it cracks.
There's some validity to that. So if you look at the ASTM
It's
standards,
about weight,
the boxes are thicker, right? But they're way heavier,
right?
but they need less steel.
Right.
Because you make this thicker, your steel can be further apart. So there's less force in that steel, so you can use less steel, make the steel smaller, but it's heavier.
Right.
So those are all constraints. You could make this thing out of solid steel, right? An inch thick, and it'd probably do the job. But who wants to deal with all of that? My point here is that all of these loads on it, even the loads through the pick holes to pick this thing up, to take it to where you're gonna go, they all induce forces, not just on that piece, but all the way around the box. You know, the weight of the center of the bottom of the box is pulling down, which is then pulling these sides in. So very important that you have the steel in the right place to make all of that work. Any questions about any of that?
Do they reinforce those holes? Because you're gonna get stress lines through them when you're picking it up. Do they reinforce them at all? Or is it strong enough that it's okay to pick up?
Those are some of the issues that we're trying to work through with them.
Really?
Because in general, they feel like they can just put these things in. They need to lift it up, so they need to put a lifting hole in.
Yeah, but then your stress lines are gonna get concentrated right around your holes.
Yeah, and the guy that's on the floor wiring that lift point in can calculate that, right?
No, oh, no. I
That's
was thinking of,
that's the problem of not
Something
having those
qualified.
things on the shop drawing.
Yeah.
Is because if the designer doesn't, if it's on the approved shop drawing, if it's on the approved shop drawing, it's been approved by the designer.
Yeah.
If it's not on the shop drawing, you can't just do whatever you want.
right,
Similarly, we're looking at this. So when you design a section like this, you think of it like a 1 foot thick piece, even though it's 10 feet long. You just take one section and you analyze that one. It's just for simplicity.
you put axial loads on it, you get your potential buckling when you're doing that.
That's engineering. Let's talk about engineering. But to do the analysis, we're just looking at a thin section. So what are they using for reinforcement steel? They're using cages or mesh, right? And that mesh is welded wire mesh. So we're going to look at this as this is the top of the box and this is the bottom. And this is not to scale. Let's call this a 1 foot section. Anyway, so each of these wires are a certain diameter. And that is what's representing this steel here. Each of these wires, called longitudinals, are only there to hold these in the right place. So this wire has been calculated to handle this load. So I need 4 lifting holes in the side of this box. So I'm going to put one here, 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 and here. And to do that, I need to cut those 2 wires. And I need to cut those 2 wires. And those 2 and those 2. Okay, so I'm in the factory. I cut those. Well, in effect 2 wires, right? But 4 places on each. And now I'm going to come back in and because I know that if I cut the wires, I need to add some steel back in. So I'm going to add some steel like that. So that's going to spread that load from that lifting loop back into the rest of the box. Is that okay?
No,
Why?
because you need to go this way too.
Yeah,
Right.
you'd still cut your ones through here.
Right.
So in this example, I have 1, 2, 3, 4, 5, 6, 7, 8 circumferential wires, and I've cut 4 of them twice. And so now I have half the steel I had before, supporting the flexure loads on this box.
So essentially the wire that's running between the holes is doing nothing.
Right. We see this all the time.
Yeah.
Like all the time, daily,
Mhm.
all the time. The best thing you could do is put bars in here going this way because you're replacing that steel.
Why'd you cut them in the first place then?
Well,
How do you, so they couldn't be in the same spot because you needed
Yeah.
that for space.
Do they almost wrap around? Or are they just,
so
No.
sometimes you need to cut them. Sometimes you could cut the transverse wires and bend them sideways because that wire is no longer holding it in place. That's the ideal because then your steel is just going like this. All it says in our bridge design plans is if you cut a wire, you have to replace it with the same area of steel. So if this wire is this big and I cut it and I replace it with a piece that's this big, I've done that, right? Yeah, it's bigger, right? So now, if trying to figure out where to draw this, if this is my wire that I cut and I needed 4 inches there, cut out. I cut it twice over here, so I'm going to cut it twice over here again. I cut 4 inches of it out. That's my grid. And so if I replace it with a bar that's twice as big in area, so now this lifting loop is, let's just say here, taking up that space, because I did cut it off because I need it. So right on the outside of that, on this 4-inch piece that I cut out, I can take a 1-inch thick bar. Plenty, right? Huge amount of steel. Way overdid it. I can put a 1-inch by 4-inch bar in there. And I've met our standard.
But it needs to connect to the other
Yeah.
wire, correct?
Does it?
That's what the design people are there for, is to,
So, but
Should.
we're not design people. We're just people working on the factory floor.
it needs to hook into the wire system.
So,
Not just be
it needs to just come down to this transverse wire like that.
at least,
So let's say that's 8 inches now. Is that good?
if we're on the factory floor, that's more than we need.
Is it? Does anybody think that an 8-inch piece of 1-inch steel rebar is going to strengthen that wire that's cut? Why not?
Needs to be longer so that you hold the stress of that lift point.
Mhm.
Needs to be at least the same length as the rest of the bars
And
or longer.
That is a great observation. Not quite right, but it's a it's a great observation. I wish you worked in all the factories. I wish that was what they saw. What happens is, to get this to be strong enough, obviously a 4-inch piece isn't going to be strong enough. It's not going to do anything. It's not engaged in this monolithic piece. It has to be long enough that it has what's called development length. And that development length changes based on the size of the bar, what kind of coating the bar is. If it's a deformed bar, or like this one, or if it is smooth bar, like you'd see in a CD basket.
yeah,
It varies on the strength of the concrete, and it matters how much cover you have on that concrete, so that when it's under tension, it just doesn't pop out the side because it's can't take it. So this is what's not understood on the factory floor, is that this development length on a piece of number 4 bar is about 18 inches from each side of the cut. So if you cut a 4-inch piece out, you need 4 inches plus 18 plus 18 to duplicate what you cut on that one bar.
40 inches right there,
So that, yeah, so that,
off a 4-inch piece.
But the specification says you just have to
and
replace what's cut.
it says you have to replace the area of steel that was cut.
So what they're thinking is just that small piece is fine.
That there's no rule that says how long it has to be.
Because
And this is why we want to see it in the shop drawing. We want to see that somebody has calculated that you can cut up to 2 wires and then replace it with whatever length of whatever steel. Addison, go first.
well, what about the cover of the concrete towards, I mean, how close can it be to that hole? You would basically almost tie it to the next rung over or something. I mean, it would have to have some sort of cover.
that's what I was wondering is, how close can you get to your next line and it be doing anything?
Or just how far away from the hole, the cover that you would need. But it might be pretty darn close to the next, yeah.
So ideally, this is all symmetrical, right? These are
Yeah.
wires on 4-inch or wires on 6-inch. So as close as you can get it to the original, the better. But
Yeah,
you are spreading, you know you're losing it, right? You know you're weakening it here.
Mhm.
And so you are spreading those forces away from it. So similarly, if you cut an entrance hole for a pipe right here, and you cut all those wires out, what do you do differently? Now you've lost my picture is not right, but let's say you lost 5 wires. And each wire has so much area of steel. You have to replace that area of steel back. You have to get the development length. So maybe it's a 2 number 4 bars all the way top to bottom. We don't know because we're not going to calculate that in the factory. Kenzie, you had something to say.
I was gonna say, like, if I'm in the mind of a factory worker and on the floor, I would see this as a problem for the shop drawing.
Right,
So
exactly.
are there going to be engineers in this class who are the shop drawing? Because this would be the best people to tell them it's not my job.
The key for this class is if it doesn't say to cut it, you cannot cut it.
Yeah.
And if you cut it, you have to have a repair detail that shows you how to repair it. An interesting case we just ran into, zoom out just a little bit if you would, Dalton. An interesting case we just ran into is a box that has a 24-inch hole in the side of it, just about like that. So they've cut all of this steel and all of this steel to get that in. Well, they do have a repair detail, and correct me if I'm wrong, Addison, but I think the repair detail says that they need reinforcement steel like this around the hole. Does that tell, and what I think it said what size too, right?
Mhm.
Didn't it say the bar size? Does that give them enough information to make that piece?
It's not, you're right on the bend. Right on the.
Or why does that not give them enough information? Can they do this?
No,
Why?
Because it's going.
When are they
across.
cutting the hole?
because it's not
Boards
in
make it
the
or
center. They're not
after?
gonna have the same amount of coverage. You
Yeah.
know what I mean?
So you
It's gonna,
you put this bar in.
yeah, it's gonna be out,
Just
outside
sticking
the
it.
box.
Where do you get your development length for the bar?
Right.
Not only that, but we've seen what's happening here in this sidewall, right? From the earth load, from the induced moments as it's loaded from the top and the bottom, we know it's gonna go this way. So we know both that inside and outside cage are important. So how much of that cage do you have in this
Not very much.
6 inches? And it is 6 inches on this drawing.
That's not gonna cut it.
So my question back to him, which then made it back to the designer, which is now being redesigned, is what do you have to put in here to even make it work? Because that's like a column, 6 inches here, you go 2 inches or an inch in for coverage, an inch in for coverage, you got 4 inches left. You're talking about like a column in a building now.
Yeah,
Then you have to ask, what are you putting through the pipe? Because that could be pushing out on it too, right there.
Yeah, that's,
Like drainage.
it's just, it's a drainage pipe. So.
Yeah.
So, okay,
But,
there
but
really won't be.
the point is they had the repair detail, but they didn't see that it would fit in the
Yeah.
piece that they're making. It has to go back to the designer. Absolutely has to. And this is a piece that's in a line of 20-ish boxes. And why not just make the box break here and then they can use their thing. But it has to go back to the designer. It can't change it at the factory to allow that. Any questions about that?
Does it say like, from the hole, how much cover there should be? Like concrete cover?
How much cover from the hole? I don't recall. It would be the same as our spec where it's an inch or inch and a half or whatever it says for the rest of
yeah.
it. But what they could also do in situations like this, let me go back to the lifting hole one. So they've cut 2 wires. And actually, we had this problem in Des Moines a few years ago. They cut 2 wires to put in a lifting hook of some kind. And then they were going to put in more reinforcing on the next circumferential over to beef that up here and here. And they didn't have enough room to the top of the box to get the development length from where they cut. So now they only, let's say they had 10 inches here and they needed 16, they needed 18, whatever it was. Another thing that they can do is they can put in a hooked bar. This. And that will, there's a calculation, there's tables you can look up and you can see that this hook is this long and this wide, then it only needs to be this long. So it's another option. It's not an option that the guy on the factory floor is going to be able to implement. It needs to go back to their detailer. My point is, it seems like you're just cutting a couple wires to put in a lifting loop, but you're not. Okay, so let's go back to, any other questions about that? Anything that doesn't make sense? Any points that brought up with anybody?
You could demo that mesh with duct tape if you wanted, because the backing or the strands and duct tape work the same exact way. Just a thought.
I'm not following you.
Duct tape has a like the cotton or nylon mesh in it, so it gives it its strength.
Oh, okay.
So if you were to poke holes in
Oh, I'm with you, yeah.
poke holes in the duct tape, you can show how it would be bad.
Yeah. And everybody has trouble getting into bags once in a while in the kitchen, right? And then the slightest little poke with a knife and the whole thing comes apart.
Mm-hmm.
Similar to that hole, it has enormous tensile strength, but you break it or you put a weak point in it and it's all gone. Let's see. So I want to do two different things. I'm trying to decide which way direction to go. We're going to look at a plan here in a minute that has a wing wall. So it's basically half a box. Okay. So you have a soil load. Nope, you have a soil load here. And the deeper you get, the bigger the load gets. You have the weight of the box here. So how are we going to reinforce that? And while you're thinking about that, little story, I talked to, I think it was a Story County engineer last week about their project. And they said that they had a project a few years ago that one of the wing walls they put in, as soon as they backfilled it, it just fell apart, just fell over. And this is an example of that. I think this is a T here. That. So where do we put reinforcement in that? Well, it's on the shop drawing, right? But if they were doing the shop drawing, where would you expect them to have reinforcement? So we have a slab here. And we're going to assume that they're going to make the slab just like they make everything else, with steel calculated for the loads, a certain distance in, a certain distance out. But what else do you need for this?
My very first thought was bracing, but I'm not familiar with the scope of where this is being used.
So that profile just is continuous. There's no bracing.
Okay.
External.
You're gonna have to definitely strengthen it up at the bottom here.
Yeah, where the,
Like L-shaped.
yeah,
Like
You can fill,
going to the bottom and
It's
coming up.
gonna wanna, it's gonna wanna kick in.
Do that both ways. Left and right.
Yeah,
like that.
Yeah.
Any other thoughts? Any thoughts about where that should be, top to bottom? Does it matter?
Well,
Well, that's where you get the math and start figuring out how big is steel, how long is steel.
ideally, I mean, it would go all the way to the top, but if you can't just have a 14-foot section of steel just hanging out up there while you pour the base. So you at least need it enough to tie on the next piece. I mean,
So what is just based on what we've talked about already, what is the minimum length that these would have to be?
well, we've mentioned 18, but we don't, I mean,
For number-
what's the word behind
For a
18?
number 4 bar, it's 18. The bigger the bar, the longer the development length.
Yeah, development length. We need it to be at least development length.
Exactly. So you need to be at least that long.
But
So that whatever it's transferring around here, right, is restricted by the concrete, by the engagement in the concrete. And here you could be on the neutral axis, right? Because you're not trying to keep the piece from bending like you are here. You're trying to keep the whole structure aligned. So yes, these bars are super critical. Sure what perspective that was about to be, but so this is now the wing wall isometrically. I'm not an artist, right?
That's why you went
So-
to school for engineer, right?
So now you have
hard to
these,
traffic.
these L bars is what they're called,
Mhm.
that go through there, and they are a given spacing and a given size that has all been calculated. And so first of all, let's go back to concrete. So what happens now if we calculated out the size of these bars, the development length, and Joe, QC guy decides, I'm not gonna take an aggregate moisture today. We're just gonna run it, see how it looks. And they batch their concrete and say, oh, that's good enough. We're gonna take a little water out of it in the next load, but that's good enough. Let's go ahead and pour this in there. So they do that, and we know that it rained and rained and rained for the last week. We know that aggregate's completely saturated. And they didn't do an aggregate moisture, so they just batched whatever last time's moisture was. What's the end result?
So if it's too high in moisture, it'll be,
You have more of like a cream on top of that mix, wouldn't you?
yeah,
It'd be less.
Your
more-
water cement ratio is higher.
it's kind of,
So we know that it needs a certain, and that we'll cover this in the other section class, but we know that there needs to be a certain amount of water in there for the cement to hydrate and do its job. And we know that any more water than that we get, weakens it. So now we've calculated for the correct development length, but instead of 3,000 PSI concrete, we have 1,800 PSI concrete.
because it's wet,
What happens to that bar?
more and bigger.
Well, it can't, we're not gonna change the bar design, right? So what happens is it doesn't have enough strength to hold that bar back.
Yeah, the bar's gonna come out of it.
And it's gonna pull the bar out of the concrete, right? So that's one problem. Another problem is they have to pick this thing up. I guess I still drew it wrong. They have to pick this thing up. How are they gonna do that? Well, we need a lifting loop here and here so that we can hook the crane onto it and lift it up. So let's get rid of that bar. We don't need that one. Well,
Why are they putting the lifting loops in the
that's what they do.
bottom?
What they do.
And put them in the top.
It's just what they do. I don't know. Vicky, do you have any contribution there?
Like, because it's stronger down there.
I'm assuming they do it on both sides.
That way they don't.
That's, yeah, I would think so.
Yeah, they'd have to,
You mean here and here?
Yeah.
right?
I don't know. So anyway, we know that they're gonna cut some L bars. So before I was in materials, I was still in design, but by that point in the summer, I was kind of hanging out with the materials folks. And I went over to East Des Moines plant to pick up some cylinders for Vicky. And this exact same thing was being built at the time. They had 13 1-inch bars, L bars in the bottom of here. And they cut, is it 6? I think they cut 6 to put in the lifting loops that they needed to pick this thing up. So six out of 13 they just cut.
So my question is,
They're in the way of the lifting loop
when they're designing it, why don't they implement these holes prior?
because they don't know how the factory is going to produce it is the short answer.
Okay,
But between the factory and the designer, they need to get that figured out ahead of time.
yeah,
So I'm still waiting to hear back from the Story County engineer, but he said that he thought that was in about 2018, which is when about this would have been made. So I'm really excited to hear if that is the one that failed. But they looked at it, and the reason that it failed is because it didn't have the L bars that it needed, and so they backfilled it, and the thing broke in half. So point is, once they cover it up, we have no idea what's inside of it. We have no idea if they did it right. So anyway, important little details like, oh, there's supposed to be L bars in that wing wall, make a huge difference. I'm gonna go back to my box culvert here. And then we'll call it quits. But, so back to my box culvert, we have these things called haunches that go in here, right? That's part of the, just erased my bar, but you get the idea.
What my TV looked like back when I was a kid.
That's right. So why do you suppose that these haunches are, so this is the cage, this inside line is the cage. Why do you suppose they put the haunches in like that?
it'll resist the moment.
Mhm. And so on the plans, there'll be, I'm lost, I'm sorry. So that's the cage. So on the plans, there'll be a bar or a notation to put the bar in that's haunch steel that goes across here maybe every foot or so. They're pretty small bars, but it helps get that moment around the corner and avoid stress concentration in the corners.
Mhm.
So again, when you're inspecting these things, you want to make sure the haunch bars are in the right place. You want to make sure that they're long enough that they get some embedment in here. That's not a development-like thing. They'll say haunch steel at foot centers, number 3 bars at foot centers. They have to go past the first cage, but don't protrude into the outside or something. This is how they spec that out. But they're very important bars because that's what gets that around the corner. So it helps get that moment transferred into the sidewall.
Yeah.
Also, when we look at the plan, you'll see that the area of steel here is different than the area of steel here, is different than here, is different here, different here, different here. Because of all those calculations they've done, it's a different area of steel. Sometimes they just go for worst case scenario and put the max area of steel they need everywhere. Sometimes they'll build sheets that have, so these are transverse bars now, not the important ones. But so they'll put the important ones, let's say this is the center top of the box or something. They'll put bars like that in the center top, and then they'll change the spacing here because they don't need as much. And so then they'll bend it. Let's say they bend it here. And so it complies where it needs to, but they save steel where they don't need it more over here because it takes more right here than it does right here. So they'll figure that out and they'll actually build the steel sheet to match what they need for areas of steel in those right places.
That's kind of what it looks like, but they're actually, I think they're using they're using like a flat cage for the one face where they need more steel.
Mm-hmm.
And then they're using a cage that wraps around too, but they're using them on the same face, you know, the outside or inside where they need it.
And so then if you add up that area of steel, then it meets the.
It does, yes.
And we'll look at that on plans. So I'm just gonna take it one more step here. We made haunches in there. I'm gonna make a box that looks like a stop sign. And so nope. Can't geometry either. So where are we gonna need steel in this? Let's just start with top and bottom. That's easiest, right?
Yeah.
There's a load where we need steel.
Right along that top and bottom.
The bottom edge there, yeah.
If we're gonna pick it up, we need it here, right? Because the load's in this way.
Yeah.
So let's just assume there's the same there. And we know we did it in the sides because it transfers, right? Where else? We put a haunch bar.
Yep, all the way across, get it
All the way
corner.
across.
All right,
And then
so we might as well do this, right? So
We have each one of your corners, right, too. Wouldn't,
here. So you'd put like mini haunch
yeah,
within the mini,
yeah, like-
in the mini corners.
yeah, if your corner's coming like this, you know, you got it going like that.
So my point of this whole thing is
You got a lot of steel.
you basically have it all the way around.
Yeah.
Now, if it's a circle, where do we put it?
all the way around.
Same around, right?
Cause it could be on they could use it on any side too. I mean, it's not designed to be up and down or, you know, whichever way.
If it's a circle.
Yeah.
You have no stress concentration there. So
Well, even if it
run
was,
all the way around it.
even if it was an octagon or whatever, it could still be used this way. And that, I mean, you could put a mark on up here or whatever, but
So I want to be I want to expand on that. So
Yeah.
this box that has this area of steel here, 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 and here,
Yeah.
those are not the same top and bottom. You can't put it in upside down.
no, not the box.
It only goes one way.
Yeah,
But a pipe you can.
Yeah.
Right? So same concepts that we've been talking about with beams applies to the pipe. So when you do a 3-inch bearing test, 3 edges are like that. It's not quite like the beam, but it's close. So where do these break? Where are you gonna see the cracks when you load that.
On the edges, or outside edges.
The in,
Okay, I heard outside edges, that's here
Yeah.
and here,
the inside, top and bottom.
inside, top and bottom, exactly. So if you were not gonna put two cages in, if you were only gonna put one cage in,
Is
if
it
you're
gonna
only
be,
gonna, let me rephrase that.
Yeah,
If you're only gonna put steel where you needed it, where would you put the steel?
well, now it has to have a direction then, wouldn't it? If you're trying to minimize your steel placement, then you would have to say, hey, this side goes up.
yeah,
Because we have steel on the inside, on the top and bottom, and outside on the sides. Is that right?
Yes. So we've made that notation on the outside of the pipe, this side up. Where do we put the steel?
close to those 4 points that you have where it's gonna break.
So steel goes here, here, and here, and here, right? Is that what you're saying?
Yes.
Yeah.
Yes. Everybody agree? I agree. So now if we're gonna make a cage that did that, we would just connect those points, right? I mean, that's the easiest, is to just roll a cage that's kind of elliptical,
Yeah,
right?
elliptical.
That's actually allowed by STM. Nobody does it. I don't know why anybody would do it. But it's actually allowed to have an elliptical cage. You just have to control your spacings there, 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 and there. And you have to mark it this
Top
on
or bottom.
top. Can't just even though it's round, you can't just put it in whichever direction you want.
And that's why they don't do that.
That's why they don't do it.
It'd be
They have
harder to.
The weird thing, I mean, they could totally, they're marking it anyway as certified and pipe class size, everything. They could just as well add that to their stencil.
They-
Forklift drivers, they wouldn't be able to put them in stack
Yeah.
well enough.
Right, so you gotta see the machine when they're the vertical ones that make them,
Well, yeah, you'd have to
know.
you'd have to know.
They'd have to keep track of it, so
They would.
somebody would have to keep.
It'd be a big curve in the industry, so you'd have to tell everyone, this is exactly how it has to be placed and used the entire time.
Well, and they do have lifting holes in them to pick them up, right?
Hmm.
So what does that mean? Let's say they put the lifting hole in the top, right here.
Yeah.
Where's the steel need to go?
Around that.
Here. Yeah. Luckily, it's not the same amount of force you need to lift up the pipe as it is you need to drive over the top of the pipe. So it ends up not mattering.
You can tell, like, for instance, when you go to mid states, what the top of the pipe is, because that's where their forks are.
Oh,
They pick it up.
that's very true. Yeah. So anyway, it is allowed by STM to do an elliptical, or elliptical pipe cage. You do have to mark which end is top. The reason they don't do that is because it's way easier to make them round and then not care which way is top. So because of that, you might have one cage, you might have two, but if we go back to, let's say you have one cage and it's in the middle. And we have cover, so we're protecting the steel. You can imagine from our original beam description and where the neutral axis is, the area that doesn't have any force is between where the steel is and where the outside skin is. So really, they just have too much concrete in some places. And then they have cover. But Addison and I were at brand X, since we don't like to name names. We were at brand X and we look at the bottom of the pipe where you can see where that steel cage was sitting. And you have little witness marks of those longitudinals that are closer at one side, which then would mean they're further away
Yeah.
at the other side. So what does that do to pipe strength? That vastly affects the strength of that pipe, right?
Yeah, you're gonna be a lot
Weakens
weaker
it.
at once.
Weakens it.
Because your steel's in the wrong spot. And their attitude was like, it's not off that much. It doesn't matter. It's all covered. You have cover on it. So why does it matter that it's off a little
But
bit?
are you getting the?
Well, it matters
Are you getting the
because,
required amount of cover?
yeah. So at least with these, we can break them, right? We can put them in a 3H bearing test. We can load them up. We can see if they perform the way they say they're going to perform. And most of the time, at most plants, the concrete strength's higher than it needs to be. The pipe is stronger than it needs to be. We don't have problems, but you can see if the compressive strength of the concrete was low, if the cage is placed wrong, if everything is wrong, you could get a problem. Luckily on pipe, we can break it and we can see if there's a problem. On boxes, on wing walls, we have no testing. All we can do is measure it, and that's the importance of pre-pour and post-pour, following the directions. Does that make sense?
Yep.
Does it make sense how I related the box to the pipe?
For sure.
Because everybody's like, well, why does the cage go in the middle of the pipe? Because that is a little bit different.
Well, your breaking points are at different locations versus horizontal and vertical. So you're accounting for both of those.
Well, the way I look at it is the pipe's just thicker than it really needed to be. If you're making this for the space shuttle, you wouldn't make it that's the same thickness of pipe all the way around. You'd make it thicker where it needed to be thicker and thinner where it needed to be thinner, right? I'm not quite sure I brought you guys all along with that concept. But does that make sense or not? Okay. Just kind of getting burnt out maybe. Okay, so I have some drawings, and because of the time, and we have another meeting at 10, I want to just look at those real quick. So, but now when you see these shapes and you think, oh, it's a broom handle and it's round because we're going to be sweeping in any direction. I mean, I pulled in today and I backed in and I looked forward and I'm looking at fence posts and a pallet and I'm like, that's why they designed the pallet that way with 2 layers tied together with beams. So this strong that direction with the minimum materials they can get. That's why the fence post is shaped like this, so that they get that channel. It's rigid both directions, minimum amount of material. Hopefully you guys will start seeing that same similarities, I guess. All right, I'm gonna turn the camera off and share screen real quick. It must be this one. So here's the call out for the strength where you have the different areas of steel in the different locations, what that area needs to be. So if they cut that plate, and this is inches per square inches per foot. So again, they're analyzing it as only a foot wide. But each of these wires ends up to be that big of an area. So if they cut the AS3, they need to replace it with a bar that has 1.38 square inches or larger in that foot. And then here's where it details those different mats. So this outside bottom, I'm guessing, without reading it really close, is that AS8. The AS2 is on the, well, here they have 2 layers, so that's a little more complicated. But anyway, you can see where it calls out how much area of steel in each location is required. And then here where they have overlaps, it'll also call out on the plan what that overlap length is. Why is that important? That's where the development length is happening. You can't just butt the 2 sheets up together because then there would be no reinforcement there, even though they're touching. This one actually calls out lifting holes, but it doesn't show you the details if you would have to cut the circumferential steel to add that. It doesn't show those details in here. The overall picture for this is so each box section here, it shows your lifting holes on the top here. It shows how your wing walls come out at 45s.
Those tie steel too.
Say that again?
Tie steel on the sides, how they're tying
This
them.
one? Yeah. Tie bars is what they're generally called. So they have a hole in each one and then a threaded bar that goes in there to pull them together. There's a bunch of notes here, of course, and then here it shows where those tie bar holes go. Some details about that weird joint between the wing wall and the barrel sections. Here's where it's showing how thick each wall should be, 10 inch, 10 inch, and 8 inch, 8 inch. And there's tolerances to that. So when you're inspecting these, we would look at those tolerances.
On the steel there at the haunch, it doesn't necessarily show the bars that we're gonna be using.
Yeah, it'll show it somewhere.
Okay.
So here it just shows the size of the haunch.
Yeah.
And that there's 4 of them, 1 in each corner.
Yeah. But the steel's right next to it.
So clearances at 1.5 inches, including top.
Yeah, for between.
I was thinking it was a 1 inch, but go by the shop drawing. There it shows the shapes. Okay, so here's where it gets a little more into the reinforcing details.
For the head walls, yeah.
Oh, right. All right, so this is the one I wanted to zoom into. Can't I move that? So here's where it shows the L bars, number 5s. Okay. Number 5 bar is at 12 inches on center for those L bars, and they go along the mat on the side into the bottom and then along the bottom mat here. So that's something that we'd be checking for. Number 5 bar is 12 inches on center. So that's one that goes clear across the bottom. So every 12 inches into the page. Number 6 at 8 inches on center. So this one here is bigger and closer together. It goes across this top. The circles that go into the page are noted here. So those are just number 4s, 12 inches on center. So that's that one, that one, that one, that one, that one, that one, that one. And then same on the top. So I'm not seeing, oh, okay, so the other L bar is called out up here, which is a number 6 bar. So it's bigger than the number 5. That's something that we would check for. Did they use the right bar in the right location?
Yeah.
8 inches on center. So not only is it bigger, but there's more of them more often. And that one goes down here to the bottom mat and over. So we're going to verify all those details when we're looking at that to make sure it doesn't fall over when they backfill it. And then to tie all that together, of course, they need something to tie it to. So they're using number 4 bars, 12 inches on center, all the way down going into the page. They're wanting 2 inches of clearance between the outside skin and the mat. And then they're wanting 3/4 inch chamfers on all the edges. So they're not square sharp edges, they're tapered. And it has a bracket and all of the details on that bracket, you can just measure with a tape measure.
The way that it looked up there on that is it looks like it's just gonna stand up that steel. The bent steel is just gonna stand up 14 foot tall. That's what it looks like to me. While they
Yes,
that base.
I didn't think of that. You're right. So it didn't say how long they need to be. It does show it all the way to the end.
Yeah.
And then you would expect it to be cut off, 2 inches down or whatever that clearance is.
Yeah.
Same on the ends. Hello. So this is just another one. And then, so it is a signed job drawing. It's signed by an engineer. So if I saw something I questioned, like there's no L bars in this wing wall, you might want to get a hold of them. However, they're taking the responsibility for this being done correctly. And so then this section gets into, oh, this is another.
Yeah, I know.
The other. I don't know why they have that in there twice. This is getting into the analysis of the whole thing. We're not gonna care about that. And then here it goes into the steel details. And this is where you'll find where those haunch bars are. Maybe not this
Right.
one.
That's, yeah. Maybe.
It should be detailed on there somewhere. Sorry, now I'm just scanning through here.
Will they always have steel in them, or are there times, or there might not be?
In the haunches,
Mhm.
I think they always have it. This is an example of how they custom make the mesh so that it has the required areas of steel in the right places. Closer together, further apart where they need less of it. And really all our job is, all the factory floor guys' job is to make sure that what they're using matches what the shop drawing is. So in diameter of wire, spacing of wire, and then of course, when it's in the mold, that it's in the right place, thickness wise. I'm surprised. I
No haunch bar.
I just can't see the haunches. Sorry, I'm sure they're there.
Okay.
Doesn't look like it.
Isn't it like if the bars are continuous, like if there's a development length, then you don't really need bars across the haunches because the development length is already holding onto them.
Okay, you're talking about if the sheet is bent and it wraps around the corner. I still think they put haunch steel in there for that
They do,
extra reinforcement.
And they will.
but it's not, it's
Huh?
Just not there.
You've looked at these then and you know that it's not there?
no, they haven't made many yet. They haven't made one since I've been there, but
Yeah, usually you'll see the dashed line across here. That's definitely something to ask about.
okay.
So
Wow.
anyway, that's as deep as I want to get into looking at the shop drawings, but I guess the important part is, as we looked at on the board, it's important as far as placement, it's important as far as size, it's important as far as not cutting it and changing the intent of the steel, unless there is a detail that shows how to repair it if you cut it. And then taking these shop drawings ahead of time and sitting down with them so that you really understand what is supposed to be where before you go in to the factory on the floor and start questioning why they're doing something. One thing I hear a lot is, oh, we put extra steel in it. Yeah, we cut it, but we put extra steel in it. Well, how do you know how much extra steel it needs and where it needs it? So that's one of the things that we want to try and get across in the class is it has to match the shop drawing because none of us know.
More's better, right?
No.
That's what they think.
Yeah. I showed you the picture of the highway, right?
You can't have too much steel.
But you're right. That is what they think. Questions? So what I'd like from everybody is if you want to send me some notes on what worked well, what didn't work well, what you'd like to see as far as more details, what I spent too much time on, not enough time on, I'd appreciate that feedback. Thank you very much for coming and
Thanks for
wasting an hour and 45 minutes.
Good job, Mike.
Thanks.
Takes a lot.
Is it not recording? I expected this. Oh, there it is. Stop recording.